Good evening. Welcome back, everyone. We now move on to the second technical session of day three of the 6-day ATAL sponsored online faculty development program on advancements in cloud and edge computing, research, and industry perspectives. The second session focuses on highly relevant topic cloud in education, which explores how cloud technologies are transforming teaching learning processes, academic administration, and digital education ecosystems. It gives me great pleasure to introduce our second resource person for the day, Dr. Ramani Baivi, Professor and Head, Department of Computer Science and Engineering at Adishankara Institute of Engineering and Technology, Kerala. Ma'am brings with her rich academic experience, strong leadership, and deep insight into integrating cloud technologies in higher education. Her session will provide valuable perspectives on leveraging cloud platforms for effective teaching, learning, and institutional growth. Ma'am, we are truly honored to have you with us. I kindly invite you to take over the session and share your expertise on cloud in education. Thank you, and over to you, ma'am.
Thank you, Shani. First, let me apologize for my sore throat. It got infected yesterday evening, unfortunately. But no, I tend to crack my throat further to make this session effective and useful for all the participants here. I need your wholehearted support and cooperation in participating in this session. And whenever there is a discussion, I want all of your involvement because, as Shani said, this is a high relevant topic for all of us, including us. The inaugural, during the inauguration, I told we had a purpose for proposing this FDP as we want to learn, then adapt ourselves into the cloud technology for the sustainable growth for the faculty members, students, and the education sector as whole. Let me share my screen. Um, whatever I speak, if that is not clear to you, or if my voice is so feeble, you are unable to hear, please let me know. I shall take care of it. Screen visible to everyone? Hello.
Yes, ma'am, it's visible. Yes, ma'am.
Okay. Okay. Cloud in education. Again, for now, for the first few minutes, again, we'll be talking about cloud. Then slowly we'll get into the agenda of this session. Let us understand what is cloud. Cloud, we all know well that it is an infrastructure. For example, when we take, if I want to light my room or house, I need to only, just, you know, uh, switch on, just press on the switch. So if I just make it on, then I'll get the service will be provided to me. I need not to go on and generate electricity or build the power plant for getting the current or the electricity. So that is one utility. Or you can participate in generating the electricity, or you can participate in the maintenance and distribution of the electricity to the various nodes or the client points. The cloud is also like that. You can use it, and the same electricity I can, once I'll get the electricity, I'll use that electricity for some other purpose, or I'll make it use for generating something else. I use it for my microwave for cooking. I use it for ironing my clothes. I use it for refrigeration. I use it for pumping water from well to irrigate my field. So various things I can use the forms of the electricity can be converted. I can use that. So likewise, you can either use the infrastructure, or you can create the infrastructure, or you can maintain it. So it is a choice. Again, it is a choice of having it or not. And if I am, no, no, it's my personal choice whether I can live with the electricity, or I can live without electricity. It is again a personal choice. I can live without electricity as well, but I have to be ready for that kind of life. This is so thing with cloud as well. So cloud is an inevitable infrastructure, especially in the computing world. Either we have to embrace it or not. It's our choice. Again, taking the security aspect of it, when we keep our valuables, on an earlier age, we used to keep our valuables and gold and other things in at home. We'll keep an almirah, lock it multiple times. Then we'll keep a separate room for it, and somebody will be safeguarding it. We'll keep some dogs, other things. How much more valuable that we store at home, that much care that we have to give it for safeguarding it. And we'll see that even if you go out, it will take care of its safety, so it will add certain pressure to us. And slowly, the public locker systems being offered, so we used to keep our the valuables in the public locker, that is in banks. So we can go and hire a space. Either you can go for a small locker, bigger one, and with some other attached access as well. For example, if you give some chemicals, you need to have some climate or AC attached to it. You can pay and do that. And it's the same thing. I know you can keep your valuables in the locker, and your private key is being given to you. And what you keep, what you use in that space, it is up to you, and nobody will take care of it. And whether you keep it safe or lose it, it's up to you. But there is a public security system. They will keep security of the entire thing, all the lockers. But what is inside my space, the locker, that is my responsibility. So with cloud as well, say whether I'll go for a very safe, public security, or I'll take care of my infrastructure to safeguard things on my own. So with this understanding, we shall move on to cloud in education. Okay, so I have designed this session with uh, six subsections. The first one is the technical convergence. So please pardon me. So here also will be understanding cloud and the previous sessions, like this here also, but in the academic perspective. Then industry roles. There are now in education, there are let us understand the stakeholders in the education. Obviously, the curriculum, that board of studies, it will be offered by university. Either it can be deemed to be university or central university, or no, your autonomous body. Then you have the infrastructure to deploy the curriculum, that is an institution, classrooms, labs, and other things. Then you have a people to deploy the courses, faculty members and the staff members in the lab, and other supportive staff to run the institution. Then the main stakeholder is the student. And the here, how do we embrace cloud in the perspective of students? In the second section, we are going to deal with that industry rules and the real world stack on cloud. Then coming to the campus, cloud architecture in the campus, how we can automate things, the in the campus activities and data, that we are going to discuss in the section 3. Then section 4 is a continuation of that. So what are the tools and ecosystem for the faculty members and students, for us to embrace the different technologies over the infrastructure on cloud. Then we have the curriculum design. So here again, we focus on no, indigenous, no, national-wide institutions, how the premier institutions in our nation, no, adapting, changing themselves in the growth graph along with the cloud. So we'll take certain examples and we'll move on with that. We'll learn that. Then we'll discuss on the challenges, and we'll have the summary of this session. Then we'll have an open discussion on this. So before continuing with that, let me ask. I just ask if you have a yes as if the yes is your answer, please type it in the chat window. Are you from deemed to be university? Any faculty member or student from working in or studying in deemed to be university, private universities? Yes or no? So do we have any faculty members or students studying or working in MHRD no, institution? Yes, Dr. Mayank. So that is NIT, no, IIT, Triple IT, Kottayam, like institutions. Do we have any participants from national level institutions, NITs, IITs, Triple ITs? Okay. So I understand the rest of us are working in affiliated universities, sorry, institutions affiliated to universities. Some of the institutions may be autonomous. Right. So with that understanding, we shall continue with our presentation. Okay. So cloud computing in education. Um, Today, we are not just talking about cloud as online storage or shared drives. We are talking about cloud as the engineering backbone of modern intelligence. Here, this section is very specific to take an example of AI. How do we deal with that? Now, AI growth. AI is not just a mathematics problem. It is a fundamentally a systems engineering problem. Most of the algorithms powering today's AI were invented decades ago. What changed is not the maths, it is the infrastructure. Without modern cloud computing, those equations would be still in research paper. The hardware bottleneck, hardware bottleneck is the math existed, but but the machine did not. The machine was not. In 1998, Jan LeCun introduced LeNet5, a convolutional neural network used for handwritten digit recognition for in the bank checks. It had roughly 60,000 parameters. It worked, but it could not scale to complex vision tasks like face or object recognition because CPUs could not process large matrix multiplications fast enough. But at present, the modern large language models like Gemini GPT, then other I don't know, large language models are estimated to operate at hundreds of billions to over 1 trillion parameters trained across massive GPU clusters. The real difference is it is not the better math or algorithm. In 1990s, we trained models on single core CPUs, but today AI models are trained by clustering thousands of CPUs, such as NVIDIA A100 or H100 accelerators working in parallel. So in the cost wise, in 1990, storing 1 gigabytes of data cost roughly uh, no $9,000. But today storing 1 gigabyte in cloud object storage, that is AWS, is dollar only three. That costs around about no dollar 0.022 cents. So we did not suddenly get smarter, but the computing became cheaper, faster, and massively parallel. Why AI requires cloud? Why I have taken AI? That is well known to everyone. I understand we have one participant from automobile engineering, but whatever may be the stream of engineering or any other course or any discipline that you are in, AI has its own role there. So AI workloads are bursty and infrastructure incentive by design. The training and advanced AI model may require thousands of GPUs running continuously for weeks or months. Once training is complete, you may only need a handful of machines for inference. So you cannot buy a 10,000 GPUs for a 3-month project. Um, that would bankrupt any university or company. This is exactly why cloud exists. That is elasticity. You can rent a massive compute temporarily, then scale back to a nearly zero. So the economy part is a modern AI is not downloaded and run locally. It comes consumed via REST APIs. When someone uses ChatGPT or Gemini or other things, their laptop is not doing the computation. The inference happens inside a cloud data center, and the result is returned over the network. When we take the AI versus Moore's law, traditional Moore's law predicted compute power doubling roughly every 3 years. Since 2012, AI compute usage has doubled approximately every 3 to 4 months. The standard enterprise structure cannot keep this pace. Only high-scale cloud performance can do that. So global cloud consumption trends. So money follows infrastructure demand, and AI is driving that demand. The global cloud infrastructure spending grew over 20% year on year, driven primarily by generative AI workloads. Gartner forecasts that worldwide spending on generative AI will reach no, around 700 billion in 2026 or beyond. The traditional data center, the racks, consume 5 to 10 kilowatts of power. Modern AI server racks consume 40 kilowatts or more. So this creates heat and cooling that challenges that most private data centers simply cannot handle it. The shift is the organizations are moving away from on premise or on campus data centers because AI hardware density exceeds their power and cooling limits. So only hyperscale cloud providers are engineered to operate at this level. So before going to the next session, let us have some discussion again. Okay, from the student perspective, um, let us see or let us discuss. Um, oh, Now we say IT is sinking, and the opportunities are shrinking. Now the students joining in the IT or CSC, then no, relevant branches are enormous in the market now, but yet to get placed. What could be the reason? Please share it in your chat window. So the next section we are going to deal with that. So I need to get your understanding, and I shall take some input from you so that we can discuss further on it. Or what is lacking in our students? Are or are they now industry ready? Because we are the same teachers, we are deploying the same courses, curriculum. They are getting better marks now because and everything is entire thing is available with them. So they are learning with a great ease, scoring marks. They are now cracking the competitive exams, but they are yet to be placed or they have to find some jobs. What is a gap? Or how do we prepare them? Because our main purpose of now existence in the campus is to ensure the students' growth. I shall like to get your perspective or actions on it. Can you please share? So we have faculty members. If you want, you can unmute and talk. What is lacking? What is really lacking? Any idea? Am I audible? Am I connected with you?
Yes, ma'am.
Thank you. AI encroaching most of man-made works. So that is why CSE is booming or it is sinking. I think it is a madman efforts. Okay. No, AI is everybody's talking AI. And we'll take blockchain, we'll take trusted systems, any advanced technologies that we have. Let us not stick only to AI. So AI has some, no, that will pull some controversy. Let us not focus on that. What is really lacking with our system, education system? The key pointer is if I develop something or if I run my code or if I develop something, it works for me. It will work in my machine, but it will not work everywhere. That is the gap. That is what lacking. So we have to first equip ourselves and then train our students. So whatever we do, it should be work. It should work everywhere. Let us start using cloud. Once we accept that cloud is infrastructure, the next question becomes very practical. What jobs are our students actually going into? The industry did not just rename roles. The cloud computing changed what engineering work looks like on daily basis. In the past, the teams were divided cleanly. The system administrators managed servers. Then the developers wrote code. Then the data scientists trained models. In cloud era, these boundaries were collapsed. The traditional roles, but still relevant, but expanded. We had system administrator, network engineer, backend developer, front-end developer. These roles still exist, but today they are expected to automate, scale, and design for failure. The cloud native roles are they design systems for highly availability, is a then disaster recovery from day one. This includes multi-zone deployments, automated failover, and recovery objectives. So DevOps engineers and owns the delivery pipeline from source code to production. He manages CI and CD, that is continuous integration and continuous development, containers, infrastructure automation, and system reliability. Then MLOps engineer sits at the intersection of data science and DevOps, responsible for deploying models, monitoring drift, managing training pipelines, and scaling inferences. So we are no longer training students for isolated jobs. So we have to train them for systems ownership. The placement opportunities and market demand. Hiring is based on deployment ability, not just coding ability. When companies interview graduates today, they don't ask only, can you write code? They ask, can you deploy this reliably? So there's a high demand skill areas. Infrastructure as code. Tools like Terraform and Ansible allow engineers to define servers, networks, and permissions using the code. This eliminates manual configuration and ensures reproducibility. If infrastructure cannot be created from code, then it is not production ready. Then containerization or orchestration, Docker packages applications with their dependencies. Kubernetes automates deployments, scaling, and recovery. So this is now standard production, not an advanced specialization. The serverless computing. No, I do not want to repeat the same thing. Just will get into the industry what they say. So when it works on my machine, it's no longer acceptable because production is no longer your machine. Over 90% of organizations now use containers in production, and automated CI/CD pipelines are the norm rather than the exceptions now. Real world value generation. The cloud skills translate directly into speed, scale, and cost efficiency. This slide answers the unspoken answers from the management. Why should we invest in this? Right? So it's a scalability. Cloud systems are designed to serve one user to 1 million users using the same code base. Auto scaling groups add or remove compute automatically based on demand. This is not a feature, it is the default expectation in modern systems. So, what is a speed to market? The provisioning infrastructure used to take weeks or months due to the procurement and setup. In the cloud, the same environment can be created in minutes using APIs. This fundamentally changes how fast innovation can happen. Then, how do we optimize the cost? The traditional IT requires capex, the large upfront hardware purchases. Cloud operates on OPEX, pay only for what you use. So, this lowers entry barriers for setups, research teams, and educational institutions. Cloud engineering is not about tools, it is about delivering val- delivering value faster at scale and with less risk. Okay. Now let us get into the cloud architecture in the campus. Um, okay, so I shall invite your input on this. What is your understanding or expectation or perspective in automating um, the campus? Hello, can you respond in a chat window or you can unmute and talk?
Ma'am, you mean to say that office automation like leave particulars or the students' information systems also some of the colleges they're using. That is
Yes, sir.
attendance
Yes, sir.
point of
Right,
view
sir.
and
Right,
subject
right,
is.
right. Yes, that is LMS, the learning management system. It is on cloud, on ERP. Yes, sir. Then, and obviously, almost all the institutions, they are, being
Because
converted
the
their.
nowadays college also procuring action, that is a material management one side, then
Yes,
the
sir.
man management and finance management, everything in see the college itself or university itself. So everything is computerized, that if you want to remove or don't want to invest money on the hardware side, you can make use of clouds. See,
Exactly.
whatever you are doing, that can be implemented by using cloud computing. That's it.
Yes, sir. Yes, sir. Now, what I say, so we have highly invested laboratories in our campus. Now, there are certain workstations, i7 machines, GPU machines. Are we utilize them effectively? Whether the investments are converted into profits?
Yeah. That is to be audited every now and then frequently. For if it is not utilized properly, then we have to replace that system with some other alternative way. See,
So,
nowadays all smart systems used, smart classroom, then smart library, something like that. So that type of things we have to go on or move
yes, sir.
on.
Yes, sir. I agree upon with you. For the LMS and the teaching learning process, mainly we use all now cloud services. But now with respect to infrastructure that we have invested on, whether we are utilizing it effectively. Now there are mostly they are underutilized. Still, we are running the toy problems, both in the regular practicals and projects, and unfortunately in research as well, because we don't utilize them. So in that case, instead of further invest, as you rightly said, first thing is we have to put all the infrastructure into a centralized thing, put it on, purchase a cloud space, share these resources, and whoever wants, need it, we can provide the services to them. So we can make money out of it, or we can make profit out of it. Then second thing is, so instead of investing further for taking up high-end researches, investing on the hardware, because these hardware after 5 to 10 years it will become totally obsolete, and you cannot make anything out of it. But you can, with the invest a little on cloud, you can use it with a you can utilize it, and you can for all our purposes. So this is the main
Sorry, I
plan.
just like to interrupt you,
uh,
ma'am. And though it is a new system and not going about an absolute system,
mhm.
the same lab might be used by many courses or many faculties. Each faculty will install their own system. Say Java, they will install one teacher, and Python they install another teacher. The same system will be bearing all operating system. Finally, we will not make use of these systems optimistically. Sometimes it will not work to any of the faculties. That sort
Yeah.
of problem is arising.
I understand, sir, but that is only for 8 hours or 9 hours in a day. What
No,
about?
ma'am, because of that, the system itself not working.
Okay.
It's a confused state. Yeah.
Okay, that is a that is a different aspect of it. I'm telling we have the infrastructure, but whether we can, are you ensuring it is utility? Because we have well equipped infrastructure with us, it is completely working, whether we are utilizing it 100% or not. And if for any further need comes in, instead of investing further on it, we'll go for low cost investments on cloud. So with this understanding, let us move on to the next session. So let us move from industry into our own environment, that is university campus. I'm not going to detail on much on this, because almost all the campuses are using this ERP LMS system, and the campus ERP system works fine 95% of the year. The real test is exam ready day. The real test is exam ready when we, so this we can really encounter this problem in the even the university, when the students or all of us are registering on the exam day, when the massive load is put on the system, now how that is responding to it. So that is a no problem with this. So when tens of thousands of students log in at the same time, the cloud architecture is about designing for that 5% peak time without wasting money the remaining 95% of the year. So mainly the core architecture has present. I'm not getting into the ERP system, but I'm taking the architecture of ERP system, the presentation layer, application layer, and database layer. So here in the presentation layer, we have the static content, HTML, CSS, JavaScript, then all the front end contents, notices, PDF is served through content delivery network, CDN. The CDN catches content closer to user, reducing latency and protecting backend servers from the traffic spikes. This means the application servers are not wasting CPU cycles serving static files. The application layer, in the application layer, the ERP application runs on a pool of virtual machines behind a load balancer. When the traffic increases, the auto scaling launches new instances automatically. When traffic drops, the excess instances are terminated. On a result day, the capacity scales up automatically. At midnight, it scales down, back down. So there is a dynamic scaling up and scaling down. Then the database layer, the database runs on a managed cloud database service with automated backups, point in time recovery, and read replicas for reporting and dashboards. This removes the single biggest op, no, operational risk, that is a manual database management. So here we don't build for average load, we build for peak load and let the cloud absorb the shock. Again, this is virtual labs, that is virtual development interface and DAS, desktop as a service. Again, we are well aware of it. I'm not going to do much on that. The high-end lab hardware is expensive to buy, maintain, and refresh. Every institution faces the same problem. The GPU-based labs are expensive and they become obsolete every 3 to 4 years. Actually, I was little optimistic to say earlier that 10 to 5 years, but it is only 3 to 4 years only. And the cloud flips this problem. Instead of buying machines, we stream machines. Applications like AutoCAD, SolidWorks, Unity, or simulation tools require high CPU, GPU, large memory, and frequent upgrades. Most students do not own laptops capable of running them smoothly. The cloud solution for DAS is we have Mini, Amazon Upstream 2.0, Azure Virtual Desktop. So this means 30,000 laptop can access 3 lakh workstation at a time. Implementations inside us, the pre-built lab image ons, the scale desktops during the lab hours, shut them down during after the hours. Virtual labs turn hardware no, lacking or unavailability into scaling problem, and scaling is what cloud does its best. The research infrastructure. The research compute is bursty. The cloud matches that pattern perfectly. The research workloads does not need constant superpower computing power. They need short bursts of massive compute, often right before the deadlines. Buying hardware for peak research demand is financially inefficient. The cloud provides the cloud providers offer spot instances which use unused capacity at discounts of up to 90%. These ideals for batch processing, these are the ideals for batch processing simulations, training models with checkpoints. The trade-off is interruption, but research workloads are designed to cover it. So when we take the big data, Amazon EMR, that is Elastic MapReduce, runs distributed frameworks like Apache Spark for large-scale data pre-processing and processing. Clusters can be created in minutes and terminated when work is done. Databricks provides a unified and uniform platform for data engineering, analytics, and machine learning. widely used in academic and industry research. Then the storage life cycle management deals with the active research data which stays in hot storage, that is live storage. Completed or infrequently accessed data is moved automatically to cold or active status. This reduces storage cost without deleting valuable research outputs. The cloud allows university to rent a supercomputer for a week instead of buying one for 10 years. So this is the tools and ecosystem. So this is in this section. So what are the we tend to explore what are the different tools, and these tools are already being discussed in the previous sections as well. So I just go fastly in this section. So one of the biggest hidden problems in technical education is not the syllabus. It is the environment setup. The students spend weeks installing software, fixing dependency issues, and debugging configuration problems before they write a single line of meaningful code. Cloud-based developer tools eliminate this friction completely. And we know all the Google Colab, then GitHub code spaces. So what is the bottleneck with Google Colab? So that can be taken care in the GitHub code space. Then here, this solves the classical classroom problem. When we start using those cloud spaces, so the student tend to say it works on my system, but not on yours. He cannot say that, right? So it has the educational impact. Zero installation time, no OS compatibility issues, then faster transition from theory to practice. When the environment disappears as a problem, then the learning accelerates. And the well-known environment for us is a learning management system. So the platform that we use is Google Classroom, Canvas, Moodle Cloud. The teaching at scale requires systems, not spreadsheets. As class sizes grow, the teaching becomes more blended. The manual tracking simply does not scale. The modern LMS platforms act as the operating system of education. So here again, we use the integration of SSO or through then analytical tools for the warehouse BigQuery to analyze the student performances. Those are the well-known or standard LMS that we use. Once the learning is digital, then it becomes measurable. So the technical tool showcase. So, I have taken the broader classification of academic domain. The different departments have different needs, but the cloud pattern remains the same. The browser-based access, scalable backends, and zero local setup. The computer science, we use Docker Hub, Firebase. The students learn how real applications are built and deployed today. And the electronics mechanical, they'll normally use MATLAB, SimScale. These systems or services remove the dependency on physical labs for many simulation heavy courses. The biotechnology life sciences, So they'll use AlphaFold via Collab. It's accessible through cloud notebooks, enables protein structure prediction without owning GPU hardware. The advanced research grade tools are now accessible even at the undergraduate level. Let us be aware of it. These are not optional add-ons. These tools are the modern laboratory. Okay, before getting into the next section, our curriculum design, I wish the participants' attention here. Whether no, is there any requirement or need to revisit or revamp or restructure our curriculum? If so, and which as aspect of it? Share your experiences, perspective on thoughts. As the current curriculum, is that okay? Is good enough to make our students industry ready, or should we make any upgradations? If at all we upgrade, and what are the things that we can do that? Please share your thoughts. Okay, let me ask like this. We have computer networks, operating system, other core subjects. Do we have cloud computing as a core subject? Is an inevitable course for every student to learn? Please respond if you have that in your curriculum. Instead of an optional course, do we have a cloud or cloud-based courses as a regular or courses for all the students? Any faculty member in this forum can respond to this. Yes, we have in our syllabus, these are subjects are the core subjects. Or do we have any labs, cloud-based or cloud-equipped? Let us not say that, no, we have the drives, so we store the programs, not able to view your so comment. Not able to view yours, so comment. So I didn't get. What you're not able to view? Oh, no comment. Okay, okay. Okay. Okay, thank you for responding, sir. At least get, even if it is something, no, also good answer. So that will break the waiting state. Thank you, sir. So here, how do we migrate, or how do we transform our or restructure our curriculum cloud equipped so that our students will become industry ready? Cloud is the key pointer. It is not the optional. Let us now get into it. the next session, let us now discuss on this. At this point, the question is no longer whether cloud should be taught. The real question is how seriously it should be taught. To answer that, we look at what technical institutions are already doing. Let us not take no, no, the universities in abroad. So already they have revamped their structures. But our premier institutions in our nations, like IIT Bombay and IIT Delhi, so I'll be sharing this now presentation with you. So we have the syllabus link. So whenever you get an opportunity, if you're autonomous or if you have anything to university to suggestions that you can do to your university, so you can look at these syllabuses and suggest the university to include uh, such kind of courses as a core subjects. The IIT Bombay, the virtualize the course, the pure operating system is being converted into virtualization and cloud computing. Can we believe that? Uh, so they teach how to build a cloud rather than how to use it. So for which they have framed the syllabus. So the students learn how hypervisors, containers, then cloud abstractions actually work, how to build a cloud, not just use one. In IIT Delhi, they introduced a subject, cloud computing technology fundamentals, uh, through which they introduce cloud computing, data center design, software defined networks (SDN), and data center designs. IIT Madras, cloud and distributed systems are integrated directly into degree programs, especially with VS in data science. We all know well that IIT Madras is offering a bachelor program online in data science, uh, where cloud native and distributed data processing are treated as foundational skills. The insight here is when IITs teach Kubernetes and virtualization and SDN as core system knowledge, we cannot restrict ourselves to the definitions of SAS and PAS. So here the regulatory mandates, AICT and UCG alignment. The cloud computing is no longer optional. It is explicitly encouraged by regulators. Sorry. There is often a concern that adding cloud courses may conflict with regulatory frameworks. In reality, the opposite is true. The ICT explicitly lists distributed and cloud systems as a recommended as a micro specialization. Some universities, they say minor course with 18 credits. Yes, it is clearly signaling that cloud and distributed systems are employability critical skills. The UCG guidelines provide frameworks for programs like BCA, MCA, which emphasize open electives in emerging technologies, explicitly introducing cloud computing. So institutions are encouraged to offer flexible, skill-oriented electives aligned with industry demand. So teaching cloud is not a deviation from policy. It is a direct response to it. So here is a proposed course curriculum. So there are 4 units. The first unit, the virtualization layer, cloud architecture, then the cloud native and DevOps, data and AI on cloud. Then how do we deal with the technical topics and practical outputs are listed out and on the proposed curriculum. So we can take this reference is also being given. So when I share this presentation, I wish all of you to explore these details further through these links shared. So build a serverless function triggered by file uploads to cloud storage. So when we teach file operations, let us teach how do we run file operations on cloud. Then a lab implementation strategy, zero cost to low cost model. The biggest misconception is that the cloud education is expensive. In practice, public cloud education programs make it cheaper than physical labs. So we have certain free trials for, especially for students. Say AWS Academy, it provides structured curricula and free learner labs, typically with $100 cloud credits per student, so without requiring credit cards. Then Google Cloud Skill Boost offers ready-made. I think most of the institutions are having Google Developers Clubs through which the cloud certifications are offered. Please encourage our students to take up those certifications seriously. This now Google Cloud offers ready-made cloud labs that runs on real cloud infrastructure. Students learn by doing, not by simulation. Then GitHub Student Developer Pack. The students are free to access cloud credits, Azure and DigitalOcean, then developer tools and platforms. Do not attempt to build a local private cloud unless you have a dedicated system team to take care of it. Use public cloud free trials for teaching. Then assessment model. We must assess engineering ability, not memorization. Traditional exams test recall. No, so exams only the the memorization or recall. The cloud engineering must test execution. So in the midterm assessments, we can have architecture diagrams with respect to scenarios being taken. All fundamentals can be taken. But we can have uh, two assessments, midterm assessment on the concept level, then end term assessment on the deployment level. The students are given work code and asked to do it, deploy it, scale it, expose it via public endpoints. It's happening in premier institutions. That is why the students are now, the industries are waiting at their gate for their students. No marks for writing codes that never runs. Why this works? The project-based assessment aligns with industry hiring practices, real-world engineering workflows, outcome-based educational models. When students graduate, they should be able to ship, not to just explain. So here now one example question that we can ask. Don't write the code. Here is a Python script. Deploy it on a load balanced auto scaling group and show me the URL working. So another deployment challenge that we can give us suggest a final exam format where a student must deploy a live URL. If the URL works on your phone, they'll pass. If it crashes, again they'll debug, they'll make it work. They should make it work. This mimics the real industry pressure on them. Okay. So before getting into the next session, let us discuss what are the challenges no transforming our campus, upgrading our curriculum into a cloud arena. What are the challenges that we can encounter? So could you please share your thoughts, experiences? Sorry, sir, Kumarasamy sir, I'm just seeing your comment. Elective subject is based on national interest and for national deployment purpose. Yes, sir, we have open electives. Uh, the students are you know, uh, encouraged to take open elective of their choice. But there are certain courses we have to make them as mandatory, irregular courses. So that is what we discussed. Now let us get into the aspect of challenges. So any challenge that we can encounter if we go for it. Can you
Ma'am,
anticipate?
slide is not changed. It is a assessment model is a display.
Yes, sir. Next slide, I'm keeping it waiting. We'll discuss and I'll move on to the next slide. You want to convert. So, for example, if you want to conduct a cloud-based lab, what are the challenges that we can expect? Any thoughts? Or let me ask this. Any of the faculty member uh, conducting a lab course on cloud? I'm asking about cloud programming or cloud computing. Normally, we don't touch upon cloud computing, though we teach cloud computing. We'll focus more on its architecture level discussions. Actually, cloud computing is much easier than our application development coding. It as a cloud, now we all know well that no, it is an infrastructure. So we are given with certain resources. So these resource and privileges. So we have to identify the resources with some, you know, uh, identification numbers or the key terms. So they look little complex. They only look little complex, but dealing is so simple. Like if you take a machine coding, if you use all the port IDs, they'll learn as Outlook, it looks so complex, we cannot deal with that. It is so simple because not much logic in it. Now we need to use the resources. Then as per the policies, we have to compute the policies. So whenever we use it, we and uh, when after our completion, we revamp, no, we close it, store it, then we lock it, will come out. No, so these are simple things before we start and after we do it. Cloud computing is much simpler. Only thing is we need to know how to use the resources with its configuration and doing, you know, programming or computing on cloud is safer. But if you have to make a system configuration efficiently, if you make it, then you can keep everything safer on the cloud. So with this understanding, let us move on to the next session of the uh, presentation. So here, the challenge that we have is at this stage, the idea of moving labs and systems to the cloud sounds exciting, but we must be honest, there are real implementation challenges. The good news is these are all not academic problems, these are engineering problems. And the cloud ecosystem already has standard solutions. Certain challenges we have: bandwidth, budgeting, and security. So in the bandwidth, if our network is weak, the cloud labs won't fail slowly. That most of us might have encountered it or experienced it. They will fail loudly. They will not, no, their failure is not subtle. They fail loudly in front of the students. On a particular day, when we start our any international programs or national level challenge, we can and experience such bottlenecks. But here that depends upon the, I'm not talking about the internet. Internet, we need to have sufficient bandwidth. But when we on cloud, if you don't do good load balancing, then we have to face its challenge. Then budget, this is not optional. You know, it is not a question of whether you can live with the electricity or not. We are living with electricity. How much you are going to use it? So that is a question. Or it again is a personal choice. I prefer to live with that electricity, that I prefer to have such a lifestyle. Go for it. But here it is not an optional, because and it is not optional for the BOS. It is not optional for the institution, or it is not optional for the faculty. It is because we have to ensure our students' growth. We do not have options. The budget alarms are the seatbelts of cloud adoptions. So we have to make it tight, ride it faster. Then security, the faculty and the student must understand shared responsibility model. The cloud provider secures the cloud, that is data centers, physical infrastructure. We secure what we put in the cloud. It's like we have the locker in banks, the accounts, permissions, data configurations. The cloud is not insecure. The misconfiguration is insecure. How much you take care of your personal locker, to whom you share it, how much protection, how you keep the data, no, your valuables, how do you take it out, how safely you take it out, use it, how safely you keep it back. So in that pathway, you have to take care of it. Then the summary and we'll call to action. Let me end this with a practical call to action, because cloud education only matters when we change what we do in our classrooms. So we have this high responsibility. We don't need a full curriculum overall to begin. We need one concrete step in the next semester. What is faculty goal, student goal, institution goal? The faculty goal is to move one assignment or lab into cloud this semester. It could be a collab notebook, already we are experiencing it. Then a code space based lab or small deployment task. That is a gap that we have. It must be real one. The student goal is obtain one foundational cloud certification. This creates a measurable employability signal and forces the students to learn cloud vocabulary the industry expects. The institutional goal is to integrate cloud architecture concepts into the syllabus review and the infrastructure. It is not what just not ask what is SaaS and PaaS, but VPS, IAM, containers, CI/CDs, and deployment thinking. If you do these things, cloud stops being a topic and becomes a capability. Thank you all. So with this, I close my presentation. We have a few minutes for discussion.
Dear participants, if you have any query, you can post it in the chat box or you can unmute and ask it directly to the resource person.
Please excuse me for 2 minutes. Let me take a sip of water. Some of the key pointers that we discuss here are yet to be experienced in our campus as well. So this study would explore and give us some directions in this direction.
So I hope there is no more queries on this particular topic. Thank you, ma'am, for delivering such an informative session. It was highly insightful and beneficial. Thank you so much, ma'am.
Yeah, thank you. And thank you all for tolerating my voice and my presentation. Thank you. Thank you so much.
Dear participants, the feedback link is posted in your WhatsApp group. The link will be active for the next 30 minutes. Kindly fill in. Thank you so much. See you all tomorrow at 6 o'clock, 6 p.m. Thank you.